In this video cast, we'll look at empirical formulas and molecular formulas. Empirical formulas, as we learned in Chapter 2, tell us the relative numbers of atoms of each element a compound contains. Thus, the empirical formula is the simplest ratio of the number of atoms to each other in a compound. For example, in H2O, there are always 2 hydrogens for every 1 oxygen. This is the simplest whole number ratio of hydrogens to oxygens. The ratio of the number of moles of each element in a compound gives the subscripts in a compound's empirical formula. And the mole concept provides a way of calculating the empirical formulas of substances as shown in the next examples. In this example, we have ascorbic acid, or vitamin C, and we're told that it contains 40.92% carbon, 4.85% hydrogen, and 54% oxygen by mass. What is the empirical formula of ascorbic acid? The empirical formula would give us the simplest whole number ratio of carbons to hydrogens to oxygen atoms. And since a mole is simply a whole bunch of atoms, it gives us the mole ratio of carbons to hydrogens to oxygens. To do this type of problem, the first thing we need to do is make an assumption. And since we're given the percentage analysis of carbons, hydrogens, and oxygens, it's simple to assume a 100-gram sample. If we assume a 100-gram sample, we therefore have 40.92 grams of carbon. We have 4.85 grams of hydrogen, and we have 54.5 grams of oxygen. Once we've assumed that 100-gram sample, now we take those grams and we convert them to moles. Take those samples and convert them to moles. And if you remember from last video cast, converting from mass to mole, we put the moles on the top of the ratio and the molar mass on the bottom. Or in this case, it's the atomic mass since it's just individual elements. In 1 mole of carbon, there are 12 grams. Where did I get that 12? Well, if you look on the periodic table, carbon has an atomic mass of 12.01. Hydrogen, when we convert that, has an atomic mass of 1. And oxygen, when we convert that, has an atomic mass of 16. And we'll use those masses to convert them to moles. In 1 mole of hydrogen, as we just looked up, there's 1 gram. And in 1 mole of oxygen, there are 16 grams. Once I convert each one of these to to moles, then I find out that there are 3.407 moles of carbon. There are 4.54 moles of hydrogen, and there are 3.406 moles of oxygen. Once I've assumed the 100-gram sample and then converted them all to moles, then I take a look at each one of these numbers of moles and find out which one is the smallest. Because I want the simplest whole number ratio now, I take each one of these numbers and divide it by the smallest number of the number of moles of all the samples. The smallest number I see here is 3.406. So I'll divide each of these by 3.406. When I do that, I find out that there's going to be 1 carbon, 1 oxygen, and you might end up rounding just a little bit. I know this isn't exactly 1, but it's going to be pretty darn close to 1. This one's going to be pretty darn close to 1. Well, it is going to be 1 because it's the same exact number. And this one turns out to be 1.333 repeating. And so my ratios of carbons to hydrogens to oxygen is a 1 to 1.3333 to 1 ratio. And if I wrote the compound or the formula using these, I'd write it as C1 H 1.333 repeating O1. But you know as well as I do that you can't have a third of an atom of hydrogen. And so what I need to do is make these subscripts be whole numbers. And to do that, what I could do is take each one of these subscripts, in this case, multiply it by 3. If I multiply it by 3, then I end up with C3H4O3. And this is the simplest whole number ratio of carbons to hydrogens to oxygens. Sometimes these numbers just turn out to be simple whole numbers. Sometimes they turn out to be a number and a fraction, and then I just need to decide what number I can multiply it by to get the simplest whole number ratio. This is called the empirical, or the simplest ratio of atoms or moles of carbons to hydrogens to oxygens. Well, if this is the simplest ratio, what do you call a formula that has the actual numbers of the atoms in a compound? Let's take a look at this next sample problem and we'll see how to do it. It says that acetylene, a hydrocarbon that occurs in small amounts in crude oil, has an empirical formula of C3H4. C3H4. The experimentally determined molecular weight for this substance is 121 AMU, or it could be 121 grams per mole of the compound as well, because remember, atomic mass units are for atoms of it, and then if we all the atoms of it, but then if we look in terms of moles of atoms, it becomes grams. What is the molecular formula for acetylene? Well, we have to understand that what we're looking for now is the molecular formula. And the way that molecular and empirical formulas are related is that the subscripts of the molecular formula of a substance are always a whole number multiple of the corresponding substances in the empirical formula. For example, if the empirical formula of water were H2O, which it is, the molecular formula is also 2 H's to 1 O. But let's say, for example, that the molecular formula was H2 or H4O2, then we'd say that the ratio would still be 2 to 1, twice as many, but this would end up being the molecular formula because it would be the true or actual formula. This is a poor example because that substance doesn't really exist, but perhaps you get the idea that you'd actually multiply each of these subscripts by 2. So the formula that we want to use is that a whole number multiple that we'd use on the subscripts of the empirical formula is equal to the molecular weight, or the molecular mass, divided by the empirical formula weight. Or the empirical formula mass. So to find the whole number multiple for this compound, acetylene, what we do is add up the C3H4, because that would tell us our empirical formula weight, and then we're told that the molecular formula weight is 121, and then we could find the whole number multiple and multiply the subscript 3 and the subscript 4 by that multiple to get our actual molecular formula. So to find the whole number multiple, I'll just call it number right here, the molecular weight is 121, and I'll divide that by the empirical formula weight. And how do I find that? Well, it's C3H4, and every carbon has an atomic mass of 12. I can find that by looking on the periodic table and looking right here. Notice carbon has an atomic mass of 12. And then add that to the hydrogen, and remember hydrogen has an atomic mass of 1. Or 1.008, but we'll round it. So I need to multiply this by 3 because there's 3 carbons. Add to that hydrogen's atomic mass, which is 1, and multiply that by 4 because there's 4 hydrogens. So 12 times 3 is 36 plus 4 is 40. So our empirical formula mass would be 40 AMUs. We put that in here for the empirical formula mass, so I'd put 40 in here, and notice I'm going to end up rounding just a little bit to get a simple whole number. And 120 divided by 40 turns out to be a multiple of about 3. It actually is like 3.011 or something like that, but I round it to the simplest whole number ratio, which is about 3. Now I take this 3 and I multiply the subscripts by that. So 3 times 3 would be 9. So my formula would end up being C9H 3 times 4, 12. And this is my molecular formula for acetylene, C9H12. Let's look at a combined problem now that forces us, first of all, to find the empirical formula, and then after I do that, to find the molecular formula. So this one says ethylene glycol, the substance used in automobile antifreeze, is composed of 38% carbon, 9% hydrogen, and 51% oxygen by mass. Its molar mass of the whole molecule is 62 grams per mole. 62 grams per mole. First of all, what is the empirical formula? Second of all, what is the molecular formula? So first thing we do is assume a 100-gram sample. So 38.7 grams of carbon. Next, I'll assume that there are a 100-gram sample, which means 9.7 grams of hydrogen. And lastly, 51.6 grams of oxygen. Once I've done that assumption, convert each of these to moles. So I'll put grams of carbon in the position where it's going to cancel, and moles of carbon is my new set of units. And in 1 mole there's 12 grams. I get the 12 from the periodic table. Remember, carbon has an atomic mass right here of 12. And then I'll get hydrogens and oxygens off there as well. Oxygen 16. And if you forgot, hydrogen is 1. So for hydrogen in 1 mole, there's 1 gram, and in oxygen in 1 mole, there's 16 grams. And I just need to run these through the calculator really quick. 38.7 divided by 12 is 3.225 moles. And then 9.7 divided by 1 times 1 is 9.7. And then 51.6 divided by 16 is 3.225 as well. Now I take my numbers of moles that I've found right here, and I divide each by the smallest. And it turns out that my smallest is 3.225, 3.225, 3.225. And when I do this, my numbers here turn out to be for ratios 1 to approximately 3 to approximately 1. Since 9.7 divided by 3.225 is actually like 3.0077, something like that, I'm just going to round it to 3. So my simplest whole number ratio now from carbons to hydrogens to oxygens is carbon 1, hydrogen 3, oxygen 1. And I got those numbers from right here. 1 for carbon, 3 for hydrogen, 1 for oxygen. This is my empirical formula. So that answers letter A. What is the empirical formula for ethylene glycol? And then if I want to find the molecular formula, remember what I'm going to do is then I'm going to use the formula up here that the whole number multiple is equal to the molecular weight divided by the empirical formula weight. So my molecular weight, I'm told in the question, is 62.1 grams per mole. So I'll write that down, 62.1, and I'll divide that by my formula weight of my empirical formula. So 12 for carbon, 1 for hydrogen, which is 3, and then 16 for oxygen, and that turns out to be 31 grams per mole. So 62 divided by 31 gives me approximately 2. And remember, I'll take this whole number now and multiply it by each one of the subscripts. And so my molecular formula is now equal to C2H6O2. This is the molecular formula for ethylene glycol. Good luck with your empirical and molecular formula problems.